We'll start the program exactly 9:30.
Okay, sir. There is no problem in PowerPoint presentation, right?
Yes, I'm very nice, sir.
I'm proceeding through the slides, sir.
Okay, it's good, very good, sir.
Okay, sir. Okay, thank you. Fine.
Okay, thank you, Vignesh. Thank you.
Okay.
Mahesh sir. Sir, Mahesh sir.
Sir.
Sir, we'll start.
Yeah. Yes.
One minute, sir. Vignesh sir.
Yes, sir.
Sir, ready start பண்ணிடலாமா sir?
பண்ணிடலாம் sir.
Okay, thank you sir. Mr. Mahesh, dear participants, today the participants is Dr. Vignesh Kumar from NIT, Karnataka, it's a Surathkal. Mr. Ramesh sir, please introduce our resource persons.
Yeah. Thank you, Saravanan sir.
Thank you, sir.
So once again, we welcome all the participants for the 1 week STTP program conducted by BVRIT Narsapur. Today our session speaker, Dr. V Vignesh Kumar. So we welcome you, sir. So Dr. Vignesh Kumar graduated from Tyagaraja College of Engineering, Madurai, Tamil Nadu, and he post-graduated in Power Systems from Tyagaraja College of Engineering, Madurai, and he obtained PhD from Department of Electrical and Electronics Engineering, National Institute of Technology, Tiruchirappalli, Tamil Nadu, and currently he is working as Assistant Professor in the Department of Electrical and Electronics Engineering, National Institute of Technology, Surathkal, Karnataka. He is having total 9 years of experience in this 5 years of teaching and 4 years of research. Presently, he is having current research power electronics applications in renewable energy systems and optimization techniques. He published many journals, IEEE, IET, and he published many papers in IEEE conferences itself. So, thanking you, sir. We welcome once again. So now I request Dr. V Vignesh Kumar sir to take over the session and deliver the lecture on application of nature-inspired optimization algorithm for MPPT in PV systems. So thank you, sir.
Thank you, sir. Saravanan sir, can I proceed?
Yes, sir, you start them, sir.
Okay. Good morning, participants. Myself, Dr. V Vignesh Kumar, Assistant Professor at NITK. So, in this session, I will be presenting or giving a presentation on the topic application of few nature-inspired optimization algorithms for MPPT in PV systems. Okay, so let us proceed on to the presentation. Saravanan sir, is my screen visible to you?
It's visible.
Okay, fine.
Okay, thank you, sir.
Thank you. So this will be the overview of my presentation. So I will be starting with a basic introduction to the photovoltaic systems, some of the basic concepts. I will be starting for a few minutes, and then I will present what are the effects of partial shading conditions on the PV system characteristics, and followed by that, what are the existing methods to mitigate these effects caused by the partial shading conditions, and then we will see what are the algorithms that are for MPPT that are available in the literature for MPPT in PV systems. So followed by that, we will see what is the significance of nature-inspired optimization algorithm and why this can be said as the promising candidate for MPPT in PV systems. So, and then we will see how to formulate MPPT as an optimization problem so that we could possibly apply these nature-inspired optimization algorithms. And after that, we will see some 3 nature-inspired optimization algorithms and how they can be suitably tailored for MPPT process. And then finally, I will talk about some modifications that can be included for the performance improvement of these nature-inspired algorithms-based MPPT process. And then finally, I will conclude the overall session. So to start with, The great motivation behind the photovoltaic power generation is one side we have increasing demand for electricity, and on the other side we have the fossil fuels which are depleting at the faster rate, and also these power generating plants that are based on the fossil fuels will cause serious environmental concerns such as emission of greenhouse gases. So naturally, we are forced to look for an alternative energy resource for the production of electricity. So some of the alternative energy resources that are available to us are solar, wind, tidal, geothermal, biomass, biogas, etc. So among these available renewable energy resources, solar is found to be the best alternative because of its attributes such as it is omnipresent, that is it will be present everywhere. It can be easily accommodated in the rooftops. It is modular type, and it will have low operational cost. That means it will not require much manpower for operating, and it requires less maintenance since it does not have any rotating parts, and ultimately it will provide eco-friendly energy conversion process. So all these factors makes the solar energy as the most popular among the available renewable energy resources. Okay. So this will be the generalized block diagram of any typical PV system, and any PV system will have all these blocks. So a PV system will have a PV source that is connected to the load through some sort of power electronic interface. And here the PV source mainly consists of a PV panel that are connected either in series or parallel combination to constitute a PV array. So, and the number of panels to be used as the PV source depends on the total demand requirement. So, PV output of the PV source will be a DC quantity, so which will be given to the DC to DC converter, and this DC to DC converter is mandatory in order to perform the MPPT process. Actually, it does the process of impedance matching, thereby to transfer the maximum power from the source to the load. So for doing that, it needs the controller, and the MPPT controller can be a digital controller like some sort of microcontrollers or FPGA based embedded controllers. So this MPPT controller will have MPPT algorithm implemented in it, and the input to this MPPT controller will be generally the PV output voltage and PV output current. So based on that, it will the MPPT algorithm will decide the duty ratio, and which will be sent to the DC-DC converter so as to track the maximum power point. And then the output of DC to DC converter will be fed into the DC to AC converter, so which converts this DC quantity into an alternating quantity, and then it will be fed into either AC loads or to the grid. Suppose that is what that is. Yes. So the block diagram that is shown here is a two-stage system in which involves a DC to DC conversion and then DC to AC conversion. So it is required if we need to export the power to grid, or if we have to supply the power to AC loads. In case if our system has only DC loads, then it is enough to have this DC to DC converter alone. So this part may not be required. So now let us look into the PV source, and we are going to concentrate in this area. So PV source to DC converter, and then how this MPPT control can be implemented with the help of nature-inspired optimization algorithm. So first let us see a bit about the operation of PV source. That means how the photovoltaic voltage is generated. So the basic unit of a PV source is a PV cell. So many PV cells are connected in series or parallel to constitute a PV array, and this PV module, and this PV, so many PV modules are again connected so as to constitute a PV array. So this is the one that we will be seeing in the large PV plants or in a rooftop PV systems. So if you look at the basic unit of PV system, that is PV cell, it is basically a PN junction device which will generate the charge carriers when it is subjected to the solar insolation. So the difference between the normal PN junction diode and this solar cell is that it will have a large surface area, and when it is exposed to the sunlight, it will deliver the current. So that means you can see here the current is leaving out of the p-type semiconductor and it is flowing through the external circuit, then again it reaches the n-type semiconductor. Whereas in the case of normal PN junction diode, forward biased PN junction diode, current will be entering into the p-type semiconductor. So let us see what makes this process, or what is the concept or principle behind this charge carrier generation and the generation of photovoltage. So for which we are going to consider the energy band diagram of the PN junction device. So we will have in the PN junction device, we will have a space charge region at the junction of p-type and n-type semiconductor, which is occupied mainly by the immobile ions. So this is responsible for the barrier potential at the junction. Now, when the sun rays are incident on this p-type PN junction device, the energy present in the photons of the sun rays will be absorbed by the electrons that are present in the atoms of this p-type and n-type materials. So what will happen is these electrons, after acquiring energy from the photons, they will get excited to some higher energy level and they will become free electrons. So it will result in the formation of free electrons. So in both the sides, p-type as well as n-type. So the electrons that are generated we call it as carriers, majority carriers in the n-type. So here the electrons that are generated in the n-type cannot move towards the p-type as it has to climb up the hill, which is a tedious task for the electrons. So electrons are tended to move easily down the hill. Okay, so this electrons in the n-type material cannot move towards the p-type material, but the electrons that are present generated in the p-type material, so we call this as minority carriers in the p-type material. So these minority carriers that are near the space charge region can easily move down the hill and it will reach the n-type material. In other words, it will be attracted by this electric field and it will get swept into the n-type material. So in the similar manner, when we say the generation of electrons, it will be always associated with the generation of holes. So here holes in the p-type material are majority carriers, and holes are like bubbles. Okay, so they cannot move down the hill, so they can easily move up the hill. So the holes in the p-type material cannot move towards the n-type material, but the holes that are created in the n-type side and are near to the space charge region will easily move into the p-type material. And also there will be some charge carriers which are formed at the region that are away from the space charge region. So these charge carriers will move randomly, and if they get a chance to come near the space charge region, they will be carried over to the opposite side. But if they don't have the chance to come back to the space charge region, they will possibly undergo recombination. So after some period of time, or the generation of the minority carriers depends on the intensity of the solar radiation that is falling over this PN junction diode. So what will happen is if the rate of generation of minority carriers is high, then that will result in the accumulation of electrons or the negative charges in the n-type and holes or positive charges in the p-type. So this difference in the this accumulation of charges will create a potential difference, and that is why we could get a positive polarity at p-type and negative polarity at the end of the n-type material. So this is what we call it as photovoltage. So now if you see, this is the thing that is responsible for the voltage at the terminals of the PV cell. Now, if you see this polarity of this photovoltage, it makes this junction forward biased. Okay, so now what will happen is the holes that are majority carriers in the p-type will try to move, or it will cross this, will overcome this barrier potential and move towards the n-type material. Similarly, the electrons which are the majority carriers in the n-type material will cross this PN junction, move towards the p-type. So this is similar to the movement of charge carriers in the forward bias diode. So there will be a current due to forward bias of PN junction with the generated voltage, and that current will have the direction from P type to N type material. Okay, so this is similar to forward bias diode, but there will be another current which is due to the movement of minority carriers. Okay, because of the incident photons. So, and that current or the rate of generation of that minority carrier is dependent on the intensity of the solar radiation that is falling over the PV or PN junction device. So that current will be moving from the N type to P type material. So because the minority carriers here, these are electrons which are moving from P type to N type, and then we will have the current direction from N type to P type. So if you compare these two currents, the net effect is that means the quantity of this minority current will be much higher compared to this forward biased diode current. So that is the reason why the net effect is the current that is flowing from N type to P type material, and we could see a current that is coming out of the P type material in the case of PN junction diode when it is subjected to illumination from the solar radiation. Okay, so if you look at the characteristics, or that is IV characteristics of the PN junction, normal PN junction diode, it will be of this kind. So the effect of PN junction device getting exposed to the solar radiation is to shift this IV curve to the fourth quadrant like this. So because it is here, because in the normal PN junction diode, we take the current direction as positive when it flows from P type to N type. But in this case, the current is net current is flowing from N type to P type. So the current direction is taken as negative. And in the first quadrant, this we say that the power is dissipated in the PN junction diode. So in the fourth quadrant, we have the power as negative. So we can call it as power that is generated. Okay. So this is the actual IV curve of the PV cell. But generally, we will require this. Arunal sir, I am experiencing some disturbances. Hello, am I audible?
Yeah, yes, sir. Yes, sir.
There is some disturbances. Can you please mute?
Yeah, Naveen Sharma. May I request Naveen Sharma, please unmute your device, sir. I request Naveen Sharma. Sir. You continue, sir.
Okay. Sir, I will mute it, sir. You can do.
Okay. So here this is the actual IV curve of the PV cell, which will be in the fourth quadrant. So, but generally we will require the characteristics of any source to be in the first quadrant. So it is for our convenience, this IV curve is represented in the first quadrant. So this is how IV curve of a typical solar cell will look like. Okay. So now if we consider this IV curve, it will behave as a constant current source in certain regions, and it will behave as a constant voltage source in another regions. So this means that it is having some sort of non-linearity, and each point in this curve corresponds to a power value. So there will be one point in the curve which will have maximum value for the power, and that point we call it as maximum power point. So this current that is corresponding to this power point is termed as IMPP, that is current at a maximum power point, and the voltage corresponding to this maximum power point is termed as VMPP, that is voltage at a maximum power point. Apart from this, there are two other specifications which will be available in the PV module. One is the short circuit current, that is current flowing through the terminals when it is short circuited, and open circuit voltage, that is the voltage measured across the terminals of PV panel when it is open circuited. So these are the specifications that you can look you can see in the any kind of PV panel. And the power rating of the PV panel corresponds to this power that is available at the maximum power point condition. So generally we often use the PV curve so that we could get the power information directly. So PV curve is again obtained from this IV curve. So if you see, this is the PV curve for uniform insolation, which is having only one single peak. Okay, so that peak point is termed as a maximum power point. And also, if you look at the behavior of this PV curve, it is dependent on the environmental conditions. Like if we change the temperature, then this maximum power is going to change. And also there will be a change in the open circuit voltage. Similarly, if there is a change in the solar insolation, then also this maximum power is going to change because of the change in the available short circuit current. So from these curves, we could observe that the PV characteristics of a PV system depends on the environmental conditions, and also the maximum power point is not going to be a constant one. It keeps on varying according to the environmental conditions. So there is a necessity to track this maximum power point or operate the PV system always at the available maximum power point. Why it is? Because we are in the capital cost of the PV system is huge, and naturally we would expect to utilize it to the full extent. So in order to extract maximum efficiency from the PV system, it is mandatory to operate the PV system at its maximum power point. So further, this maximum power point tracking problem will become complicated under partial shading conditions. Partial shading conditions are the situations under which all the PV panels will not receive uniform insolation as it is shown in these pictures. So this is because of the shading that is happening due to trees like this. Sometimes the shading may happen due to the nearby buildings like this, and sometimes it may be due to the clouds that are passing over. And this kind of shading affect a major problem, or affect mainly the performance of the large PV power plants. So it is often witnessed in the large PV power plants. And sometimes the shading is also due to the edges of the adjacent panels. Okay. So from these pictures, we could understand that whether it is a rooftop system or it is a large PV plant, this partial shading condition is inevitable. It is going to be there. And this partial shading condition will result in a huge power loss. So generally the performance of PV system is getting affected due to three reasons. One is the mismatching that is happening due to partial shading. And second is the soiling of the PV system, which means that accumulation of dust or deposition of dust particle over this PV system. And the third reason is due to the deterioration of PV panel due to aging. So among these three factors, there will be a significant loss caused by this partial shading conditions. So in order to get rid of this partial shading conditions, we need to go for efficient tracking algorithms. So let us see the effect of partial shading condition on the PV characteristics of the PV system. So consider two PV modules that are connected in series like this. One module is shaded. It means that it is receiving lesser insolation than the other module. Okay. So now this shaded module cannot deliver the power or deliver its rated power because the insolation it received is very low compared to its standard test condition. Now what will happen, this shaded module will generate only lesser amount of current compared to the unshaded module, but they both are connected in series, and in the series circuit the current has to be same. So what will happen is, if the current in the series circuit is greater than the maximum capability or maximum generating capacity of the shaded module, then this shaded module will act as the load instead of acting as the source. So the entire forward bias voltage of the unshaded module will come and appear as the reverse bias voltage across this shaded module. So that will force the current to pass through the shaded module, and the shaded module will start to dissipate power. PN junctions in the shaded module will start to dissipate the power. So this power dissipation will cause hotspots in the region of the semiconductors, which will ultimately damage this shaded module. So in order to get rid of this hotspot problem, generally bypass diodes are connected in anti-parallel manner across the PV panels. So what will happen when we connect the bypass diode like this? So when under shaded condition, this forward bias voltage that is appearing across the shaded module will now become the forward bias for this, or will make the bypass diode to be in forward biased condition. So once the bypass diode gets forward biased, it will provide the path for the current to flow through. So it will bypass the current that is flowing through the shaded module. So in that way, this shaded module will get protected from the hotspot problem. Okay, so now the effect of using this bypass diode is the creation of multiple steps in the IV curve like this. So if you see when the current is having lower value here, that means both the module will be generating the current and it will be delivering to the external circuit. So in that case, these two bypass diodes will not be in action. So the voltage across both the modules will appear across the system, terminals of the system. So we will get the full voltage range when the current is low. Okay. Now, when the current in this string started to increase, and when it comes above the maximum generated current of the shaded module, then what will happen is this bypass diode will come into the picture, and that will short circuit this path. So now the voltage that is available to the external circuit is only the voltage of this unshaded module. So that when the current goes high, we will get voltage only in this range. Okay, so this will result in multiple steps in the IV curve like this. So which will lead to multiple peaks in the PV curve like this. So among these multiple peaks, the peak which is having highest value for the power is termed as a global maximum power point, and the peak that is having and all other remaining peaks are called as local maximum power points. So because of the existence of these multiple peaks, it is sometimes or most of the times the conventional MPPT algorithms may fail to track this GMPP. So there is the need for need to develop more efficient MPPT algorithms. There are many techniques existing in the literature to mitigate this partial shading effects. So they can be grouped into 4 categories like this. First category involves modified MPPT algorithms, in which we will use the conventional MPPT algorithms or nature-inspired algorithms for tracking the global MPP. And this array configurations will utilize different configurations for PV array connections, like series, parallel, and total cross-tie connections. The PV system architecture uses different architectures for PV system, and also there is a fourth category which uses different converter topologies, like using different multi-level inverters and all those converters. So among these 4 categories, the last 3 categories are more costlier, and also they will involve more complex control, and they require more number of components. So it is for this reason this modified techniques are widely preferred, and also this modified MPPT algorithms will provide convergence to the GMPP in all the cases. And there are so many algorithms that are available in the in the literature, which will vary in the way they are implemented, and each one will have its own merits and demerits. So these algorithms can be grouped into 6 categories. The first category is the empirical methods. Under this, the algorithms such as the fractional open circuit voltage control and fractional short circuit current control will come. So if you look at the merits of these algorithms, they are very, very simple, and they will require very least number of sensors, and there will not be any oscillations in the steady state. But they cannot detect the GMPP in all the cases. And the second category is the perturbation methods, which is basically the perturb and observe method, or the incremental conductance method. And they are also very simple, and they can provide extremely high tracking speed, but they are incapable of converging to GMPP. And the third one is the model-based methods. It will use the mathematical model of a PV system, and it will have a better tracking speed. But the problem is it is highly dependent on the PV characteristics, and it is also complex. Moreover, these mathematical models will require the insolation and the temperature data for their operation. So we need to have irradiance and temperature sensors. And fourth one is the artificial intelligence method, under which the fuzzy logic based techniques and or neural network based techniques will come. So they can be also be able to track the GMPP and provide better tracking speed. But again, they are also highly dependent on the PV characteristics and are complex. And moreover, they requires the system knowledge from the expert for training the data or framing or for framing the rule base. So that is the most important part, and that is a tedious one. Final fifth one, we are having evolutionary computing methods under which our nature-inspired algorithms will fall. So here, the merits are these algorithms are they can track the GMPP and they are highly independent of the PV array. That is one of the major advantage. They will look at the system as a black box. So we will see later in the later part of this presentation how they are working. And the tracking speed is comparatively low, but it will not be it is can be overcome by improving the parameters by performing some fine tuning or by doing some sort of modifications in the algorithm. And the final one is scanning based methods, which will also have high tracking speed and tracks GMPP. And here the algorithm will track or will scan the entire PV curve in order to find the GMPP. And because of that, there will be stress on the of the stress applied on the system that are used in the DC-DC converter of this problem of these methods. Okay. Yes. So let us see what makes this nature-inspired algorithms to be a most promising candidate for the PV systems. It is their inherent ability to handle nonlinear and multimodal objective function, which is an important property to possess when we have multiple peaks in the objective function. Okay, then they are also they can provide guaranteed convergence to the global maximum point, and they are completely system independent, which means they can be used for any kind of engineering applications. So this is there are well established literature works which proves this concept. So you can see nature-inspired algorithms that are applied to mechanical engineering, civil engineering, and electrical engineering problems and all. Okay, so next, they are also free from complex derivatives. The computations involved in this nature-inspired algorithms are generally, mostly it will be addition, subtraction, multiplication, and division kind of thing. So we need not do any we need not find the derivatives, unlike the conventional or classical optimization problem. They're also less sensitive to the initial values, and they do not require large amount of enumeration memory when it is implemented in the digital platform. They can combine the rules and randomness to imitate the natural phenomenon. So these attributes makes the nature or will tell the significance of the nature-inspired algorithms and why it can be or they are effective in handling the multimodal objective functions. Okay, now let us move on to the application of nature-inspired algorithms for MPPT problem. So before that, we will see what is the system that we are going to use to employ our MPPT algorithms and test it. Okay, so this is the block diagram of the MPPT employed PV system. Here we have PV array that is connected to the load through a DC-DC converter. This PV array that is the power output of the PV array is sensed and is given to the MPPT controller, in which the MPPT algorithm is implemented. This MPPT algorithm will determine the duty ratio that is corresponding to this maximum power point, and that duty ratio value will be sent to the PWM module in this controller. Then the PWM module will generate the duty ratio and is fed into the DC-DC converter, which will then be capable of tracking the maximum power point. So the basic principle behind this is impedance matching. So this DC-DC converter matches the impedance of this PV array to the load at this maximum power point. So we need to we need to formulate the problem, and that means we need to have the objective function for any optimization problem. So in this case, we have the objective function like this: maximize PPV, which is the function of duty ratio. So here we are making the duty ratio as the control parameter, and which is again that is the PV power is the function of duty ratio. So by controlling the duty ratio, we are going to track or change the power output of the PV array, and this is subjected to the duty ratio and this constraint, that is duty ratio should be greater than the D minimum value and it should be less than the maximum limit. And we are going to consider two PV configuration for testing our PV algorithms, that is MPPT algorithms. So first configuration is a 5 series PV configuration, which will have 5 PV modules that are connected in series like this. So and each and this 5 series configuration is subjected to 2 different shading patterns like this. So these shading patterns are obtained by making the solar insolation level to be having a different values. So here you can see the G represents the insolation levels, which will be of different kind for both these patterns. So G equal to 1 represents solar insolation level of 1 kilowatt per meter squared. And the PV curves corresponding to these two shading patterns are obtained from the MATLAB, and it is shown here like this. You could see the PV curve for shading corresponding to shading pattern 1 will have 4 peaks, among which the GMPP is having the value of 60.91 watts, and it is present in the middle. But in the case of shading pattern 2, the PV curve will again have 4 peaks, but the GMPP is at the leftmost side and having the peak value of 37.43 watts. And the next configuration that is considered is the 3 series 2 parallel PV configuration. So here 2 type of configurations are considered in order to prove that this nature-inspired algorithms based MPPT are independent of the PV configuration. Okay, so now here this 3 series 2 parallel will have 3 PV modules that are connected in series, and 2 such strings are again connected in parallel. So that is why the name 3 series 2 parallel. And again, these 3 series 2 parallel configuration is also subjected to 2 different shading patterns, and the PV curves obtained are shown and named here as pattern 3 and pattern 4. So as you can see here, the pattern 3 is having a GMPP of 45.67 watt, and it is present in the middle. And the GMPP for pattern 4 is having 31.73 watts, which is present at the rightmost end. Okay, so again, these patterns are made such that the GMPP is present at different locations. That is also again to test the effectiveness of MPP algorithm in irrespective of whether it is capable to track the GMPP irrespective of its positions. Okay, so now we will see how to use this nature-inspired optimization algorithm for the MPPT process in the PV system, and we are going to look into 3 kind of nature-inspired optimization algorithm. First one is particle swarm optimization based MPPT method, and then second one is cuckoo search algorithm based MPPT method, and finally the genetic algorithm based MPPT method. This particle swarm optimization method is a well-established method and it was introduced by Kennedy and Eberhardt in 1995. It was developed by inspiring the social behavior that is existing among the animals, such as birds flocking together like this. Here you can see the birds that are flocking together in a rhythm, so in search of the food. So that means there exists some sort of a communication between these birds, so that if one changes its direction, then all the other will also change its direction. So which means that there is some sort of communication or intelligence existing among them. Similarly, there is another kind of thing which is called fish schooling. So generally, fish will move in rhythm like this in order to protect themselves from the predators. So this kind of movement of fish is called as fish schooling. So again, here also there exists some sort of intelligence or communication among the fishes, fish that are moving in that are present in the fish schooling. Okay, so based on these social behaviors present in the animals, this particle swarm optimization algorithm was developed, and here this algorithm will have a population of individuals, that is each member or individual in the population is called as particles. So these particles represent a solution. So actually they are the solution for our problem. And these particles, which represent the candidate solution, shares the information gained by its own and neighbors' varying experience, so as to update their position. So it records the information from its own experience as well as from the neighbors' varying experience for moving further. So in that way, it proceed, or the particles in the population will proceed towards the global maximum power point. Now let us see the operating principles of the basic PSO method. The first step is to initialize the swarm in the solution space, and that is we need to initialize the number of particles in the solution space, and then we need to find out the fitness value for the individual particles. So let us consider a function like this f of x, and which is having variation like this with respect to its solution x. So this function is a multimodal function having so many peaks, and it is having a global maxima here. And if our objective is to find the global maxima, then first step we need to find while employing the PSO method is to initialize the population. So for which we need to take some n number of particles inside within the solution space. So and we need to these are the particles x1, x2, x3, and xn. So the difference between the conventional or traditional optimization algorithm and these kind of nature inspired algorithm is, in case of traditional optimization algorithm, we will have one solution, and based on that the optima will be located. But in this case, we will have n number of agents or solutions which will together work in parallel to find the global optimum. So here, this for all these particles, we have to evaluate the fitness value, which is nothing but the value of f of x. So that is the second step. So based on this fitness value, we need to modify the p best and the g best. So this p best term is called as particle best, and the g best term is called as global best. So p best is nothing but the best position obtained by a particular particle so far in the process. So for example, let us consider a particle I, and it is at first iteration. So here the subscript represents the particle number and the superscript represents the iteration number. So xi1 represents ith particle at the first iteration. So at the first iteration, this is the fitness value corresponding to this xi1. So the p best value for this xi will be this position, that is the value corresponding to xi1. Okay, and in the second iteration, this particle is moved to the position xi2. Okay, which is the position of ith particle at the second iteration, and the fitness value corresponding to this position is this one. So if we look or if we compare the fitness value obtained by the ith particle at the second iteration with the first iteration, the second iteration fitness value is better compared to the first iteration value. So this is the best position obtained by the ith particle so far. So now the p best for the ith particle will become equal to this position xi2. Okay, now in the second in the third iteration, this ith particle may move to this position wherein the fitness value is this much, but this fitness value is lesser compared to the previously attained best fitness value. So the p best will not get modified. So that means this is not the best position obtained by the particular ith particle so far. So this is the best position. So in the third iteration, the p best will remain same. That is, it will be equal to xi2. And in the fourth iteration, the xi ith particle, that is xi, may move to this position, which will have the fitness value. Now, this fitness value is better among, or it is greater than the best fitness value that is obtained earlier. So this at the fourth iteration, the p best value of the ith particle will be modified to this position, that is xi4. So this is how at each iteration the best position obtained by a particular particle is compared with the earlier obtained best position and is getting updated. Okay, so this is p best. Next, G best is the best position obtained among all the particles. Suppose if we consider there are at a particular iteration, say kth iteration, and if we are having say some 5 particles in our population, and each particle will have its own fitness value associated with its position, and the G best of the population in the kth iteration is the position of the particle which is having highest fitness value. So here the third particle, position of the third particle is the one that is having the highest fitness value. So for this population at kth iteration, the position of the third particle will be equal to the G best. Okay, so like this G best should be modified at every iteration corresponding to the fitness value. So after modifying the modifying the p best and the G best, we need to compute the velocity and update the position of the particles. So that can be done with the help of this velocity update equations. So here if you see, the velocity depends upon 3 terms. Okay, so one is the previous or the velocity of next iteration depends upon 3 terms. That is, one is the velocity of current iteration, and then the p best and the G best value at the current iteration. So this can be depicted like this. Suppose consider a particle I in the k minus ith iteration having a position like this. This particle had moved with the velocity Vik and obtained the position xik at kth iteration. Okay, at kth iteration, this particle I is having p best in this location and G best at this location. Now this particle will make movement for the next iteration based on 3 components. One is the component that is along the direction of the of its previous velocity, so that represents this first term. Okay. Next, another second one is the component that is along the p best direction, that represents this second term. And third component is along the direction of the G best, that represents this third term. Now the resultant movement will be along the direction of the resultant of all these 3 vectors. So if we find the resultant of all these 3 vectors, it will be along this direction, and the particle xik will make its movement towards this along this direction, and with the velocity Vik plus 1, and reach the position xik plus 1. So this is how a particular particle makes its movement, and it is the way all the particles make its movement along in the PSO algorithm. So this velocity update equation will have other parameters also, like this here. R1 is the random number and R1 auto random number. C1 and C2 are called are constants, and Wi is also constant, which will be tuned using some numerical equations. So the performance of the PSO algorithm can be improved, or the convergence time will be improved by appropriately fine-tuning these constants. So after finding the velocity, the position of the particle will be updated, and then we need to find whether all the particles have converged or not. If they have not converged, then we have to again move to the step 2, and we should repeat this process until all the particles get converged. So this is the basic principle or basic flow of a PSO method. Now let us see how it can be applied to the MPPT process. So in the MPPT process, the population size or the population or the particles in the population represents the duty ratio of the DC-DC converter. So here population size that I have taken is 6. That means we have to select 6 duty ratio within the range D min to D max. So for this duty ratio now represents the particle, and for each duty ratio we need to find what is the corresponding PV voltage and PV current, and from that we need to find what is the PV power. The PV power that corresponding to each duty ratio represents the fitness value of the duty ratio. So now we could have the fitness value for each particle. So that means we need to send the duty PWM pulses of 6 duty ratio one by one sequentially through the microcontroller. Then we need to measure the PV voltage and current, and then we need to compute the PV power, so that we will get the fitness value for the duty ratio. After the based on this fitness value, we should modify the G best and the P best of the particular particle, and then we need to compute the velocity and the position of the particle. So for velocity equation, in this the constants involved could be obtained using these expressions. So here these are the expression values for the maximum and minimum values of this constants that I have taken. So this is basically done by trial and error method, and this needs some sort of fine tuning. So it needs to be tuned depending on the system that we are employing this PSO. Okay, so after updating the position, then we have to check whether all the particles are converged. If not, then we should repeat this process again. So by this way, this PSO will be employed for MPPT, and a program is developed in the MATLAB, and it is employed for the PV configuration that we have discussed earlier, and the tracking curves obtained are shown here. So for 5S configuration, 2 shading patterns are made to exist sequentially for 20 seconds. So that means for first 20 seconds, this pattern 1 will be appearing, and after 20th second, the pattern 2 will come into the picture. So for each time, the PSO algorithm is employed. So when the pattern 1 is, for pattern 1, the PSO algorithm tracks the GMPP successfully by taking the tracking time of 15 seconds. So at 20th second, when this pattern gets changed, this PSO is capable of reinitializing, and it tracks the new GMPP, which is of 37.43 watts, and that it takes the time of 14.3 seconds. So here it should time should count from 20. Okay, so the total tracking time for pattern 2 is 14.3 seconds, and the PSO is capable of successfully tracking the GMPP of 37.43 watts. Similarly, the same kind of same PSO algorithm or PSO program is applied to 3S2P configuration, which is subjected to 2 different shading patterns, pattern 3 and pattern 4. And from this curves, you could see For pattern 3, the PSO algorithm is capable of capturing the GMPP with tracking speed or tracking time of 14.8 seconds, and pattern 4, it takes 15.1 seconds to track the GMPP of 31.73 watts. So from these results, it is we could validate that the PSO algorithm is capable of capturing the GMPP all the time. So this is how basically a PSO algorithm is used for MPPT process, and the one that I have shown here is the conventional PSO based algorithm. There are so many modified PSO techniques available in the literature. Next algorithm that we are going to see is the cuckoo search algorithm. So this cuckoo search algorithm is basically developed based on the aggressive reproduction strategy of cuckoos, and it was developed by Young and Deb in 2009. It is a recently developed developed optimization algorithm. So which is based on the breeding behavior of the cuckoo bird. So this cuckoo bird will have aggressive reproduction strategy that which is called as a brood parasitism. That means they will not hatch their own eggs; they will lay their eggs in the host bird's nest and allow the host bird to hatch their eggs. So it is depicted in this picture. So the cuckoo will approach a host bird nest, which will be guarded by the host bird, or sometimes may not be. And it will this cuckoo bird, after approaching the target nest, it will sit on the nest and it will lay its egg. This cuckoo is so intelligent that it can even mimic the color of the host bird's egg, so that the host bird could not identify which egg is its own and which egg is the cuckoo bird's egg. And after laying the egg, cuckoo bird will flew away. Sometimes while it flew away, it removes the host bird's egg also. So this is the aggressive nature of mutation probability. That means we will not perform the crossover mutation all the time. So based on the probability only, these functions will be carried out. And for the initial population size, we need to find out we need to calculate the fitness value, which is the PV output power. So that can be done by activating the DC-DC converter with each chromosome. So we will have now the fitness value for all the 6 chromosomes. So then we have to employ the elitism. Elitism is an important function, or is an important function which will be generally employed to improve the performance of the genetic algorithm. So elitism means retaining the best chromosome as such. That means that particular chromosome will not undergo selection, crossover, and mutation process. It will be directly carried over to the next generation. So we need to employ the elitism. So that means among 6 duty ratio, 1 duty ratio, which is having the best fitness value, will be directly taken to the next iteration or generation. Then we need to perform the roulette wheel selection for the remaining chromosomes and apply crossover and mutation, and then find out whether all get converged or the stopping criteria is met. And the process should be proceeded until the stopping criterion is met. So this is how the genetic algorithm can be tailored suitably for MPPT process in the PV system. And now program is developed in the MATLAB, and it is employed for 2 configurations, that PV system configuration that we have considered. So here you could see this genetic algorithm is capable of tracking the GMPP for pattern 1 within 6.8 seconds, and for pattern 2 it takes around 7 seconds. And similarly, for pattern 3 it takes around 7.3 seconds, and for pattern 4 it takes around 6.8 seconds. So here the tracking speed is somewhat reduced, and also you could see the fluctuations in the PV power is minimum when compared to the earlier stages. That means the chromosomes are getting converged more faster in the case of GA-based MPPT. Again, it is dependent on the how finely we have tuned our parameters of the algorithm. So this genetic algorithm also is also proven that it is also proven that this genetic algorithm is also capable of converging to the GMPP, irrespective of the shading patterns and the type of PV configurations. So this gives an idea about how the GA can be implemented to the MPPT process in PV systems. So all like this, we can implement any nature-inspired algorithms for MPPT process, and generally, in order to evaluate the performance of these MPPT algorithms, there are few indices that are reported in the literature. So first thing is tracking time. So it is the time taken by a particular algorithm to reach the GMPP. So this time should be low as much possible as it can be. Next index is the tracking efficiency. So it is nothing but the ratio of tracked PV power at steady state to the maximum available PV power for a particular shading pattern. So this tracking efficiency should be as high as possible. And then another parameter that is used for performance evaluation is the ripples in the PV output power during steady state. So that means it is expected for an MPPT algorithm to have less number of ripples in the steady state. So this ripples, if the algorithm takes much longer time for converging to the GMPP, then there is a possibility for the ripples to be prolonged for longer duration in the steady state curve. So which is not which is not desired performance at all. So the ripples should be kept as minimum as possible. And then dependency of PV configuration, array parameters, and shading pattern. So any MPPT algorithm is expected to be independent of the PV configuration, array parameters, and the shading pattern. So irrespective of the PV system, it should be capable of converging to the GMPP. So this only these nature-inspired algorithms possess this kind of property, and that is why it is said to be a most promising candidate for capturing the GMPP under the partial shading conditions. And another parameter or the index is energy tracking factor. So this should be as much high as possible and can be computed using this expression. Okay, so all these indices can be used for the performance evaluation of the MPPT algorithm that is employed. So not limited to this, there are so many other evaluation indices are also available in the literature which can be used, and that depends upon the system and that is the application that we are used and the number of algorithms that we are going to consider. Okay, now these MPPT algorithms based on the nature-inspired optimization techniques will have some sort of oscillations in the steady-state tracking curve, and also it will take some comparatively large time to track the GMPP. This is basically due to the population-based approach, so which can be improved by performing some modifications in the algorithm. So here are the few modifications that can be done in order to improve the performance of the nature-inspired algorithm-based MPPT process. So first one is a parameter tuning. So the parameters that are involved in the algorithms can be fine-tuned by trial and error approach. So because most of the time it involves the random numbers, so that means some sort of randomness is present in these nature-inspired algorithms, so as to imitate the exact nature of the exact behavior of the nature. So that is why some sort of randomness is incorporated, and this stochastic nature of these nature-inspired algorithms can affect its performance that is can take much longer time for the convergence, and this convergence becomes particularly very important when it is an online optimization process like this MPPT kind of thing. So that can be improved by fine-tuning the parameters. And another approach is to alter the population size. So as the iteration proceeds, we can neglect the individuals in the population which are having very low fitness values. So by this manner, one thing is we are reducing the number of particles. That means the ripples in the steady state curve of the steady state tracking curve will be reduced, and at the same time it will lead to the faster convergence. And there are many reports available in the literature which proposed a hybrid approach. That means that by combining two different nature inspired algorithms, it is possible to improve the convergence characteristics also. And another approach is a cascaded approach in which first the global search is employed. That means the population based technique is are very much effective in performing the global search. So once after a few iterations, as almost a quite percentage of the population converges to the or converges around the global optima, the population based search is stopped, and then the convergence and then the conventional techniques like perturbed observe method or incremental conductance method will be carried out from them by taking the best position obtained from the population based approach as the initial position for their search. So by this way, global search is performed first and then followed by the local search. So this could also lead to the faster convergence time for these kind of nature inspired algorithms employed for MPPT. Okay, so finally the conclusion is that nature inspired algorithms are the best candidate for MPPT process in the PV system. They can provide guaranteed convergence to the GMPP. They are independent of system configuration shading pattern. That means they will consider the system as the black box. They don't bother about the system type of system. They do not require any mathematical models like transfer function model or so, and they are completely independent of the system configuration. So it need not require any specifications of the system, like what is the open circuit voltage and all those kind of specifications and all. They can deliver high tracking efficiency compared to the conventional MPPT methods, and they are easy to implement, which means they will have the equations which involve only the very simple mathematical computations, and they very fast tracking, but they compared to the conventional algorithm, this because of this population based strategy, the tracking speed will be somewhat low, which can be improved by modifying the algorithm parameters I have discussed just now. And there will be some fluctuations in the tracking period during the tracking period. Again, that is also due to population based approach, and this effect will become negligible if we have the convergence to GMPP quicker or at a very faster rate. So this finally I conclude that these nature inspired algorithms can provide a better performance and can in improving the efficiency of the PV systems when it is applied for the MPPT process. So let me conclude my presentation here, and if you have any queries you can ask.
Dear participants, if having any query, please post the queries in the chat box. Otherwise, unmute your audio and ask and directly interact with our resource person.
Good morning, sir. Hello, Vignesh, sir. Good morning.
Good morning, sir.
Practically, in real life applications, which algorithm is used for getting maximum power for extracting PV system? from the
practically in most of the PV system, perturb and observe methods are used, sir. If you see in any of the PV plants, but this optimized nature inspired algorithms can be effectively used under possible conditions. So among these perfect setting conditions, if you ask me to say which one is better, it depends upon the how much fine tune we are doing for the parameters. So basically speaking, any algorithms is capable of tracking the GMPP, but the convergence time matters. So that depends upon how effectively we program and how effectively we fine tune the parameters.
Sorry to ask you. Convergence, I am not aware of that, sir. A word. What does it mean actually? Convergent time.
Suppose we are taking some 6 populations, 6 members in or 6 in a population. That means a 6 duty ratio. So the duty ratio, if you consider the duty ratio range for the DC-DC converter, it will be from 0 to 1 or 0 to 100%. So we are limiting. So let us take, if we fix the D minimum and D max, that solution space, we take it between 10 or 90%. So in this solution space, we are taking some 6 duty ratios. Okay, so each time we will be sending on duty ratio, and we will be we have to wait for the converter to settle. Then we should sample the voltage and current. From that we have to find out the power. Based on that, this MPPT algorithm will perform some computation. So this will happen for all the 6 duty ratios. So that will take some time, and then next iteration will proceed. So this for at each iteration, this sampling time will take sampling the parameters will take some time, and again computation will take some time. So and the number of iterations, as the number of iterations increase, the time it takes to reach the GMPP will also increase. Okay, so that is what meant as convergence time.
And what are the advantages of P&O method, which made it to use in practical?
Very simple, sir. It will not require much complicated thing, but that is the only reason it is implemented in the practical season. So practical system, but it will not guarantee that it will track the GMPP.
Thank you, sir.
Thank you.
Vignesh sir, another one participants asked one queries. Can PSO algorithm, genetic algorithm, and CSA can we do in learn the algorithm and implementation in Python? He asked the questions. It's doing with the help of the Python or not?
Python, if you are capable, yes, it can be done. Only thing is you have to appropriately model the PV system in the Python environment. So in any thing, it is possible. Any programming language, you can implement this MPPT algorithm. So it doesn't matter. Only thing is some sort of a programming skill is required, and you should be able to know how to instead of rather than representing it as a symboling block, how to code it in the C language.
Okay, sir. Let's see. Any other participants? Are you having any queries? Directly interact with this, sir. To unmute your audio, sir. Another one participants it's having asked the question, sir. Do we get same output results every time when we run this algorithm?
Yes, every time when you run the algorithm, the GMPP will be tracked. But only thing is there will be some slight variations in the convergence time. It is because due to the randomness that is incorporated in the all type of natural spread algorithms.
Okay, sir. It's any other participants?
Good morning, sir.
Okay.
Good morning, sir. Sir, I want to know that what is the process, because if we are using any optimization algorithm, then it will undergo the process of population and then calculating all these things. Then it will take time. So how it is performing better than the conventional algorithm like incremental conductance and perturb and all that?
Yes,
Please. Yes, sir. Can you explain the process flow, that how the duty cycle is going and how it is calculating? Like, because in the flow chart it is clear, but how it is actually implementing in the Simulink? And
Yeah.
sir, one question more I would like to ask, that while I am running the simulation, I am running for 1 second and I am taking the sampling time of microseconds. So while if we do the calculation like you have done for 40 seconds, then it will take so much of time. So how to incorporate that?
Yes. So
Thank
first, yeah, okay. So first thing is, why do we go for this nature inspired algorithm? Means we need to track the GMPP. That is the thing, because partial shading condition is going to be there in the practical systems. So, and naturally, when we go for nature inspired algorithms, the convergence time will be longer. So that is why I told that some modifications should be done. So whatever the results that I have shown here are the conventional nature inspired algorithms. Okay, that means there is no fine tune or no modifications done in that. It is basic thing. Okay, so we need to do a lot of alterations in the nature inspired algorithm so as to improve the convergence time. This is one thing. So one best approach is that is why there is no doubt that this P&O will are very faster compared to the nature inspired algorithm. But the P&O are handicapped. They cannot track the GMPP all the time. Okay, so one approach is we go for the population based search in the initial stages, say for one iteration or two iteration. Okay, so from that, at the end of second iteration, let us take the best duty ratio, which is having high fitness value, and from that duty ratio, if we perform the P&O within a fraction of seconds, it is possible to track the GMPP. Okay, that is the one way to get the quicker or faster convergence, or the best promised way for obtaining the faster convergence with the help of nature inspired algorithm. Second thing is and coming back to the question of implementation, I have not shown here how to implement the algorithm, because that is beyond the objective of this presentation, and it cannot be done with this online kind of presentations. So if I provide some hands-on approach, it will be better. So what I shown in this presentation is just an overview, and I throw some light on how to employ this nature inspired algorithms for the PV systems. And regarding the sampling time that you have fixed as in terms of some microseconds, it can be done. But when it comes to the practical implementation, we need to design the DC-DC converter such that that means the inductor, and that is the DC-DC converter will have some energy storing elements. So that should be designed with more care. So only then, after each perturbation, the settling time will be very less. So we have to take the inductor, that is, we have to take the samples, either it is a current or voltage. After this, after allowing certain settling time, in the algorithms that are in the results that I have shown, I used the settling time of 100 milliseconds. Okay, so that I verified that. I just took it in an arbitrary manner. So I got the results showing the tracking speed as say some 15 seconds, 8 seconds, and 7 seconds. If it is possible to design a DC-DC converter with less settling time, then we will be able to
Sir, can you suggest any simple book to learn about these nature-based algorithms?
nature-inspired algorithms are generally there are so many books available, but even by the authors themselves, they have provided written so many books. But what I suggest is, if you go to the IEEE site, there will be the original research paper which will be written by those authors who discovered these kind of algorithms. So that is the best source to learn these algorithms.
Thank you, sir.
Any queries?
Participants, are you having any queries? You unmute your audio and ask the questions. Sir, I think it's one participant asked the question, sir, how do you decide the optimization function?
Okay, optimization function is nothing but objective function. So what is our objective? Here our objective is to maximize the PV power, and the control variable that I have taken here is the duty ratio. So we need to that is we need to track the power by controlling the duty ratio. Sir, in some research papers or research work, you can see the control variable as the voltage. So in that case, we need to alter the voltage, PV array voltage, to track the maximum power. The difference between the duty ratio control and the voltage control, having the voltage control, is duty ratio control will not require any PI controller. So it is like directly inputting the duty ratio to the DC-DC converter from the microcontroller. But if you go for voltage control, then there also the duty ratio is going to be varied, but the corresponding duty ratio for the voltage, required voltage, is determined by the PI controller. So the additional PI controller block will be required.
Queries?
Yeah, Sharon.
Yes, sir. My sir, you wait for 2 minutes, otherwise we'll wind up them, sir. Because participants, I think it's satisfied all participants not having any queries. To say thanks to Vignesh, sir.
Thank you, sir.
My sir.
Yeah, sir.
Yes, you for what of thanks, sir.
So thank you to Dr. Vignesh Kumar, sir, for your excellent presentation towards the application nature inspired optimization algorithm for PPT in PV systems. Thank you very much. With
Thank
your
you,
excellent presentation, we know the comparative statement analysis of different algorithms, MPPT, PSO, bottom and observe, theoretical algorithm, and the nature inspired optimization algorithm. So very much motivated with your presentation, sir. And once again, I thank you, sir. So I thank you, GPRIT, for giving an excellent opportunity to conduct such events. And I thank all the participants for excellent support for making the session a grand success. Thank you, one and all.
Thank you, Vignesh, sir. You discussed a lot about this MPPT algorithm used for the different algorithm, which one is best, and what are the possibility to include this or to apply for the particular algorithm. They are discussed a lot for the single applications. You apply for the different algorithm. It's very good, sir. Thank you, sir. Thank you for your support and accepting our invitation and delivering this lecture. Once again, thank you, Vignesh. Thank you.
Thank you, sir. Thank you, sir.
Dear participants, the feedback link already is posted in this chat box as well as the WhatsApp group. It will be enabled for up to 1 hour. It's up to 12 o'clock. Please fill the feedback form. The next session will start for sharp 11:30 a.m. Thank you. We'll meet at 11:30. Thank you, Vignesh. Once again, thank you.
Thank you, sir.
Thank you.